In the previous video, we covered an overview of the attention mechanism, and in this one, we'll dive deeper into the scoring function and bring everything together to understand how attention works in sequence to sequence RNNs. There are two main types of attention: additive attention and multiplicative attention. These are sometimes called Bahdanau attention and Luong attention, named after the first authors of the papers that introduced them. The scoring function in Bahdanau attention works like this, where h of j represents the hidden state from the encoder, s of I minus 1 is the decoder's hidden state from the previous time step, and u of a, w of a, and v of a are weight matrices learned during training. Essentially, this function takes the encoder and decoder hidden states and produces a single score for each decoder time step. If this seems complex, don't worry, we'll break it down further with a visual explanation. These scores are then passed to a softmax function, which looks like this, followed by a weighted sum operation where each encoder hidden state is multiplied by its respective score. Summing this gives the attention context vector. In this architecture, the encoder is a bidirectional RNN, and the encoder vector is generated by concatenating the hidden state from both layers. Luong attention builds on Bahdanau attention by introducing additional scoring functions and modifying the architecture. Unlike Bahdanau attention, Luong attention uses only the top RNN layer's hidden state from the encoder. And in multiplicative attention, there are three possible scoring functions to choose from, where the first one is the dot scoring, which is the simplest approach, where the hidden states of the encoder are multiplied directly by the decoder's hidden state. Then there's General, a more advanced version of dot scoring, which introduces a weight matrix between the encoder and decoder hidden states. The name multiplicative attention comes from the multiplication process in both the dot and general scoring function. Finally, similar to Bahdanau attention, we have concatenation scoring. This method combines the hidden state of the encoder and decoder through addition, multiplies by a weight matrix, applies NH activation, and multiplies by another weight matrix. This produces a score for each encoder hidden state at all time steps. As with Bahdanau, these scores are passed through softmax, resulting in the attention context vector C of t, which is then used to generate the final output of the decoder. Again, if this doesn't make a lot of sense right now, don't worry about it. We'll look at it more visually step by step. Earlier, we discussed how the core idea of attention is to compute an attention weight vector that enhances the signal from the most relevant parts of the input sequence while suppressing the irrelevant parts. Now, we'll dive into the scoring functions that generate these attention weights. An attention scoring function typically takes the hidden state of the decoder and the set of hidden states from the encoder as input. Since this process is repeated at each time step on the decoder side, we only use the hidden state of the decoder at that particular time step, or the previous one in some scoring methods. The scoring function given these two inputs, that is the decoder hidden state and encoder hidden states, produces a vector that assigns a score to each of the encoder hidden states. Before looking at the matrix form, which calculates scores for all encoder hidden states at once, we'll first simplify it by examining how to score a single encoder hidden state. The first and simplest scoring method is to calculate the dot product of the two input vectors. The dot product produces a single number, which is useful, but its significance lies in what it represents. Geometrically, the dot product is the product of the lengths of the two vectors and the cosine of the angle between them, making it a measure of similarity. A smaller angle between the vectors results in a larger dot product, meaning greater similarity. In practice, we want to speed up the process by scoring all the encoder hidden states at once. This leads us to the formal mathematical definition of dot product attention. The hidden state of the current decoder time step is transposed and multiplied by the matrix of the encoder hidden states. The result is a vector of scores. While this method is simple and efficient, It assumes that the encoder and decoder share the same embedding space. So, this might work well for tasks like text summarization, where both encoder and decoder use the same language and embedding space. However, in tasks like machine translation, where different languages have their own embedding spaces, we might prefer the second scoring method, which is a slight variation of the dot product. This method generally introduces a weight matrix between the multiplication of the decoder hidden state and the encoder hidden states. The weight matrix is a linear transformation that allows the input and output to use different embeddings, and the result of this multiplication would be the weight vectors. Let us now look back at this animation and incorporate everything that we have learned about attention. At the first time step of the attention decoder, we start with an initial hidden state and the embedding of the end symbol. The decoder performs its calculation and generates a hidden state for that time step. Here we focus on the hidden state rather than the actual output of the RNN. Next, we move to the attention step by using the matrix of the encoder hidden states. We calculate the scores using a chosen method like dot product or general attention. The scores are then passed through softmax to create normalized attention weights. These weights are multiplied by the corresponding encoder hidden states, and their sum gives us the attention context vector. We then concatenate the attention context vector with the decoder hidden state for that time step. This combined vector is passed through a fully connected layer, which involves multiplying by the weight matrix WC and applying a tan H activation. The output of this layer becomes the first predicted word in the output sequence. We then move on to the second time step, using the hidden state and output from the first step to generate the next hidden state h of 5, continuing the process for subsequent time steps. At this step, we repeat the attention process. We calculate the scores, generate the weights vector, apply softmax, and apply the weights by the encoder hidden states. Summing them gives us the attention context vector for step 5. We then concatenate C5 with the decoder hidden state. Pass the combined vector through the same fully connected layer with tan H activation and produce the second word in our output sequence. This process continues for each subsequent time step until the entire output sequence is generated. This provides a complete view of how attention functions in sequence to sequence models. The third commonly used scoring method is called concat. This method uses a feed-forward neural network for scoring. To explain it simply, let's focus on scoring an encoder hidden state at the fourth decoder time step. In practice, we would score all encoder hidden states in one step by processing them as a matrix. But for simplicity, we'll look at just one. In the concat method, we concatenate the decoder hidden state and the encoder hidden state into one vector, which is then passed to a feed-forward neural network. This network has a single hidden layer, and its output is the score. The weights for this network, WA and V of A, are learned during training. Here's how the process works. We start with the concatenated vector, multiply it by WA, apply a tan H activation, and get a 2 cross 1 matrix. Then we multiply that by V of A to get the score of the encoder hidden state. Formally, the equation is as follows. H of t is the hidden state at the current decoder time step. H of s is the collection of encoder hidden states. We concatenate H of t and H of s, multiply by W of A, apply tan H, and then multiply by V of A to produce the score. In the Luong paper, there are a few differences to note. So instead of one matrix, W of A, they split it into two, W of A and U of A. Each matrix is applied separately to the decoder and encoder hidden states, respectively. The Luong paper uses the hidden state from the current time step of the decoder, while the Bahdanau paper uses the hidden state from the previous time step. And lastly, regarding the notation, in the Luong paper, h of t is the hidden state of the decoder and h of s is the hidden state of the encoder. In the Bahdanau paper, they refer to encoder hidden state as s instead of h, so the concept remains the same. With this, we've covered the entire attention process, and you now have a complete understanding of how attention mechanisms work. Let's explore some computer vision application and tasks that attention empowers. For instance, consider an image like this. The generated caption is a woman is throwing a frisbee in a park. Models that produce such captions are trained on datasets like MS COCO, which consists of around 200,000 images. Each image is associated with five captions written by humans, often sourced from services like Amazon's Mechanical Turk. For example, this image from the dataset comes with five different captions, and this is the type of data used to train models like these. Under the hood, the model is quite similar to the sequence to sequence models we've discussed earlier. In this case, the image is the input to the encoder, which generates a context vector and passes it to the decoder. The decoder then sequentially outputs the caption word by word. During this process, attention is used to focus on relevant regions of the image as each word is generated. For example, when the model is shown this image during the first step, it focuses on a specific region, white areas indicating attention. Initially, the model might focus on the wings of a bird and output a bird. As the decoder moves to the next word, it shifts its attention to the body of the bird and generates the word flying. The focus then expands to the area around the bird, describing over a body of, and in the final step, the model ignores the bird, focuses on the background to output water. The encoder in this model is a convolutional neural network that generates a set of feature vectors, with each vector corresponding to a part or feature of the image. In the paper, a VGGNet was used as the encoder, pre-trained on the ImageNet dataset. The output of the encoder is a feature map with dimensions 14 cross 14 cross 512, meaning that there are 512 features, each representing a 14 cross 14 region of the image. To create the annotation vectors for attention, each feature is flattened from a 14 cross 14 matrix to a 196 cross 1 vector. After reshaping, we end up with a 196 cross 512 matrix, meaning that there are 512 feature vectors, each consisting of 196 values. The matrix serves as our context vector for generating the caption. Even though RNNs with attention have significantly advanced the field of sequence modeling, they still come with notable limitations. For example, as the distance between words in sequences increases, the performance of RNNs tends to decrease. This happens because the sequential nature of RNNs make it difficult to capture dependencies between words that are far apart. RNNs process data sequentially, meaning that they can't be parallelized. This lack of parallelism becomes a bottleneck, especially when working with large datasets or long sequences, slowing down both training and inference times. RNNs inherently have limited memory, which makes it difficult for them to handle long range dependencies in sequences. They tend to forget information over long time steps, making them unsuitable for tasks requiring the retention of context over long sequences. Given these limitations, one potential solution is to decouple the attention mechanism from RNNs entirely. By separating the attention mechanism into smaller, independent components, we can overcome the constraints imposed by RNNs. This shift in approach leads us to the transformer model, a novel architecture that leverages self-attention mechanism to process sequences more efficiently without relying on recurrence. This is how a transformer model looks. If this doesn't make complete sense right now, don't worry, we'll dive into transformer in much more detail in the next video. In essence, attention plays a crucial role in determining which parts of the input sequence are most important. Attention mechanisms compute weights that indicate which element of the input sequence to focus on. These weights enable the model to selectively prioritize the most relevant features based on their context. Once the attention weights are calculated, they are applied to enhance the most significant features while minimizing less relevant ones. The great thing about the transformer is that, unlike sequence to sequence models, all of these calculations can happen simultaneously rather than sequentially. The parallelism significantly boosts efficiency, allowing the model to process entire sequence at once rather than word by word. Before wrapping up, let's quickly touch on the notation. In RNNs, we used X to represent the input, H for the hidden state, S for the hidden state of the target sequence, C for the context vector, and Y as the output. In the transformer model, we shift to terms like key, query, and value, which we'll explore in much more detail in the next video. So, no need to worry about it just yet. The attention mechanism is foundational to why we are seeing breakthroughs like LLMs and other advanced models today. Gaining a solid understanding of attention will help you grasp how modern AI works. I've included some great resources in the description, so be sure to check them out. If you found this video helpful, make sure to subscribe, hit the bell icon, and like the video. Feel free to drop a comment with your questions or suggestions. I'll see you in the next video. Have a good one.